My name is Fernando. I'm a PhD student here at CQT. And as Angelina said, today is going to be more on the experimental side. And it's going to be on superconducting systems, which is a very common platform now for building quantum computers. And it's going to be divided in a lot of steps, this first lecture. And at first, I'm going to start introducing you to the superconducting qubit, which is a Transmon, and how did we get to it? How do we control it? And at the end, I'm gonna do a demonstration. Actually, we recorded a demonstration at the lab on how we can do some experiments with a Transmon, with an actual Transmon that we have there. So the first thing I want to have in mind is that the qubits, they are a mathematical abstraction. You've learned already at the beginning of this week about qubits, some models, and many systems can behave like that, can behave as a qubit. As long as they have two well-defined states, you have a way of controlling these states, and that is you can pick if it's in state 0 or 1, and you have a way of measuring in which state it is after you control it, after you do your calculations. So as a first example, I'm going to show the atom as a qubit. So in chemistry, we learned that the nucleus of the atom, it is surrounded by these orbitals, electronic orbitals, that we also call electronic shells, as you see here. So I'm gonna label these shells from the lowermost energy to the higher energy by these numbers, these states here. So state 0 is the energy, is the state with the lowest energy, then state 1, then state 2, and so forth. So the electron can jump between these orbitals. And if, for example, let's first think of the example of the hydrogen atom, because it has only one electron, so it's going to be easier for us. So if this electron is, for example, in shell 1, and it jumps to shell 0, to state number 0, this surplus of energy that the electron had, it's going to be emitted in the form of light as a photon. And the energy of this photon is related to the light, to the frequency of the light. That is you can say that's the color of the light. You can obtain this by the Planck's relation here. So the energy equals h, Planck's constant, times the frequency of the photon. You can also do the reverse path. Instead of waiting for the electron to decay to the lower shell, you can shine a laser, for example, a laser with a tuned frequency on the atom, and this electron is gonna absorb the photons and jump from 0 to 1, do the reverse path. The frequency here is very important because the laser must match, the frequency of the laser must match this energy here, otherwise it will not do the jump. So you might ask, what if you keep shining the laser? For example, you know it was in 0, you shine the laser, it goes to state 1, but if you keep shining, what's going to happen? The intuitive answer is that it's going to keep absorbing photons. So it's going to jump to 2, 3, and so forth. But that doesn't happen here. It happens here. Because the energy of the second jump is different from the energy of the first jump. So to do that, you'd need to change the frequency of the laser, so the atom could respond to this new frequency. It's just like a radio station that you have to tune it to get to listen to different stations, right? So imagine you don't tune the laser again, you use only the first frequency. So we know it's not going to go to higher states. So what happens? What happens, a very curious phenomenon called simulated emission, where the electron goes back to the first shell. So the shell number 0. It is stimulated by the laser to emit another photon. So as long as the laser is on, it's going to absorb one photon and go to shell 1, then emit this photon back and go back to shell 0 and keep repeating this over and over. So we call this Rabi oscillations. And okay, but what happens if we, instead of shining the laser for a prolonged time, we cut it before it has concluded a transition? So I know it takes some time, delta t, for the electron to go from shell 0 to shell 1. What if I stop the laser in delta t divided by 2, for example? It's different from classical mechanics. In classical mechanics, you would expect this energy to be a continuum of states. So the electron would just be halfway between both. But there's no state in here halfway. There's no half state shell number half or shell number 0.1. So it cannot, where is it then? The electron is going to be in a quantum superposition of both shells 0 and 1. So that's how you build superpositions with incomplete rotations, incomplete transitions. So you can observe, you can analyze all these dynamics here in the block sphere. The block sphere is a visual representation of all possible states of a qubit. Here we put the state 0, which also call it ground state, on the top of the sphere, and state 1, the first excited state, on the bottom of the sphere. And all other points of the sphere on the surface are superpositions that are parametrized by these two angles here, the polar angle theta and the azimuthal angle phi. So you can get this expression for any superposition state in terms of these angles. And the act of driving the atom, the act of shining the laser on it, in the case of the atom, makes this state rotate around the sphere. So the Rabi oscillation is a rotation about the block sphere, changing these two angles. So let's suppose you are in a superposition state and you perform a measurement of the qubit state. For example, you measure its energy. You can get only two possible states, which is state 0 and state 1, and the qubit's going to collapse to either state with a probability that is associated to the polar angle theta. So the closer the state is to 0, the higher the probability it has to collapse to 0, and the opposite is true for state 1. Okay, so we can perfectly use atoms as qubits in the way I described here. But some researchers thought that we can use many different systems. Some researchers thought, what if we slow down the laser? The laser, it is electromagnetic oscillation of millions of billions of oscillations per second. So it's really, really fast. So they thought, if we can reduce that to a few billions of oscillations per second, that is a few gigahertz, we would be within the range of radio frequency electronics. We would be able to make these signals, these drives, instead of flying in the air like lasers, we would be able to direct them on cables, electric cables, and use filters and amplifiers and all that electronic stuff. And allied to that idea, they knew they could put circuits in quantum states. So this depends on this, I'm gonna show this. This depends on this phenomenon known as superconductivity, which is when you take a block of metal like aluminum or niobium and you put in really low temperatures, like a few Kelvin above absolute zero, this metal, it becomes superconducting. Its conductivity becomes infinite. So if you make a circuit out of it and you simulate the current, this current will flow indefinitely. It's not going to dissipate. So you can use these states of current as quantum states. And yeah, so here's an example of one superconducting circuit that was built by IBM. So we can use all these the circuits. The problem now is to find a superconducting circuit that can act as a qubit. As a first prototype, I want you to think of the resonator. There are many ways of building resonators. I brought one example, which is the planar resonator. It is made of a strip of superconducting material here at the top, which is on a slab of insulant material like sapphire, and which is also on top on another slab of superconducting material here, this thin slab at the bottom. So we can control it by coupling it. There's a copper wire here close to it, and we can send signals through this wire. And these photons, these microwave photons, not light photons anymore, that travel to the wire, they can be absorbed by the resonator. So that's how we can control it. So I want you to think of the resonator as the analog. It is the electromagnetic analog of a guitar string, a mechanical string. Because think of the guitar string, it is held at both its ends. So if you stimulate a perturbation on it, if you hit it, this perturbation will flow to both sides, will hit back and forth in these two ends. And this state, this vibration will add up to a fixed frequency of oscillation. That's how you can tune your string by changing its properties. You can change this frequency. And the same thing you can do to the resonator, because if you stimulate a current, this current is going to flow and hit back and forth here inside. And it's also going to have a fixed frequency. And you can change this frequency by changing the materials involved, by changing the shape of the resonator. There are many ways of doing that. So this is the equivalent circuit of a resonator. It's simply an inductor in parallel with a capacitor. I want you to have this picture in mind because it's going to be useful in a minute. And so we can label the states of the resonator, counting the number of photons that we've put inside of it. So if there's no current at all flowing through it, we say it's on state 0. It's a state of minimum energy. If it has one photon, state 1, 2 photons, state 2, and so forth. So there's a visible problem here with the resonator. All photons, they have the same frequency. All energies, all quantum jumps here between states, they have the same energy. So this means the photons have the same frequency. And as long as you keep sending photons, the resonator will keep absorbing them. So they're not gonna release the photons again back to the environment. So you cannot do like the atom and trap the qubit inside, trap the state in two states, 0 and 1, because it's gonna keep flowing to higher states. This means you cannot we cannot model the resonator as a two-state system, at least not trivially. So how can we do that then with the system? The solution was to add a perturbation by slicing the resonator in two halves and linking these two halves by a Josephson junction. This Josephson junction is just a barrier of oxide material, aluminum oxide, and it makes a very weak link between the two pads. The electron can still flow, the current can still flow between these two pads, but it's way harder now. And the rate at which it flows depends on the strength of the current. So it's a nonlinear element. So the equivalent circuit will be just by replacing the induction by Josephson junction, which is in parallel with the capacitance here. So what happens with the energy levels of the Transmon? You have different energies for each quantum jump. So I think I didn't even mention, but this is what we call a Transmon. It is also very commonly referred to as an artificial atom because here it reproduces the uneven energy levels of the atom. And then finally, you can select only two states, the states with 0 current and the next excited state, and perform here Rabi oscillations and control these two states and make quantum computations with it and whatever you'd like to. So now we're gonna go to the demonstration. We did a recording of a Rabi oscillation experiment that we did on a Transmon, and I'm gonna play the video for you.
Hello and welcome to the Quantum Circuits Research and Engineering Work Crew Lab, or QQ Lab for short. My name is Wei Pin and I am a summer research intern working in the lab right now. Our lab focuses on building modular hardware for studying superconducting circuits at low temperature. Without further ado, let me show you around the lab. Come on in. Let me show you one of our samples. This is a cavity and it encloses a Transmon qubit inside. These are the ports where we send the input and output signals to control the transmon inside. They allow us to communicate with the transmon. Today, I will be showing a Rabi oscillation demonstration experiment where we have one of these cavities encased within the fridge over there. This is the dilution refrigerator where we house our samples. The temperature at the base is 10 millikelvin, which is just 1% of a degree above absolute zero. The low temperatures at the base allow us to reach superconducting states. The qubit at the base is isolated, and the only connection it has with the outside world are these cables over here, which carry the control and measurement pulses. The control electronics here produce and process these signals, which can be programmed from a classical computer. This is the block sphere representation of the qubit, and since our qubit is in the fridge at a very low temperature, it has no energy, and therefore it will be initialized in the ground state. Our power Rabi experiment consists of sending in two pulses. The first pulse is a drive pulse in green, and the second pulse is a readout pulse in red. So the drive pulse is tuned to the qubit's frequency, and we keep the duration of the pulse constant while changing the power of the pulse. What the drive pulse does is it rotates the qubit away from the ground state. The higher the power of the pulse, the more the qubit rotates away from the ground state. The readout pulse moves towards the qubit and is reflected by the qubit. So in reflection, it collapses the qubit into either the first excited state or the ground state. And the voltage of the readout from the readout pulse tells us whether it has collapsed into the ground state or the first excited state. So if it has collapsed into the ground state, we get a high readout voltage. Drawing a dotted line here. If it collapses into the one state, we get a low readout voltage. So if we were to apply a drive power of 0, the qubit is in the ground state, so we will get a high readout voltage. If the qubit has been rotated by half a revolution, it will give us a low readout voltage. So we can join these 2 points together with a dotted line, and this dotted line is formed by statistically averaging over many repetitions. We can also get another point here when the qubit has rotated back to the ground state, and we can also combine these two together to get a cosine graph. So now that I've shown you how we can theoretically derive this cosine graph, I can show you how we can experimentally obtain this graph with the very qubit that is inside our fridge right now. Let's go. This is our experimental setup. The oscilloscope on the right shows the drive pulse in yellow and the readout pulse next to it in blue. The reflected signal from the readout pulse is sampled and averaged over many repetitions for each frequency. The graph shown on the monitor has the same axis as the previous graph shown on the whiteboard, readout voltage against drive power. A curve of best fit for the points is seen to be slowly taking shape after more and more points are being plotted. Finally, we can see that the curve of best fit has become a cosine graph, as explained earlier. This concludes our experiment.
Now I'll be introducing you to SQUID, which stands for Superconducting Quantum Interference Device. So Fernando just introduced artificial atoms, or transmons. don't forget that, because we'll come back to this at the end of this demo. So what is superconductivity? So for certain materials, not all materials, the electrical resistance goes to 0 below what's called the critical temperature. So this is pretty cold, and it sort of depends on which material we're talking about. So for aluminum, which is commonly used for construction of Transmons, it's about 1.75 Kelvin. Right. So we know that the resistance decreases with temperature in regular conductors because electrons and so the ions vibrate less when the temperature goes down, and the electrons faces less resistivity, so it's easier for them to conduct the current. But this superconductor is a little bit different than that because it has totally no resistance. So why is this happening? The theory is that the free electrons sort of hate each other. Some of you might have heard of Pauli exclusion principle. This is a consequence of this. But when we cool down the materials to a critical temperature, they pair up into what's called Cooper pairs, and they sort of like each other very much. So they behave as a single entity. And that means it's very easy to transfer energy from one part of the material to another. So some of the examples of superconductors are lead or aluminum, as I explained, and this monstrosity, yttrium, barium, copper oxide, commonly known as YBCO. So this is a different type of conductor, superconductor, which will be used in the demonstration later, and I'll explain more later on. So one interesting consequence of superconductivity is that, as Fernando mentioned, indefinite current. As long as you maintain the temperature below the critical temperature, the current is going to flow indefinitely, what's called supercurrent. And so it creates a magnetic field, as you might know. And in the presence of a permanent magnet, then you can levitate this superconductor in midair. And this is what's called Meissner's effect. Another interesting consequence of superconductivity is flux quantization. And this is cool because it sounds super sci-fi. So flux quantization, you might be familiar with the concept of quantization by now because you guys are learning about quantum mechanics, and quantum is like what quantization is. And so, for example, electromagnetic wave is quantized into photons. So similarly, what is quantized here is the magnetic flux. So, so as you might know, magnetic flux is just magnetic field here denoted as B going through a certain area S. So it's B dot S. So it's sort of total magnetic field across some area, right? So more generally, of course, you can express this as an integral of B dot ds. But so in a superconductor, if you consider any arbitrary loop enclosing an area, the magnetic flux going through it must be quantized. That means it must be an integral multiple of a constant. So in this case, the constant is phi naught, or flux quantum. So the magnetic flux through any area must be either 0 or 1 flux quantum or 2 flux quanta, and so on. So this flux quantum, of course, the value of it is given by h over 2e, where h is the Planck constant and e is electron charge. So now we're getting closer to a SQUID, but first I have to talk about Josephson junction. As Fernando introduced, is just a sandwich of two superconductors sandwiching a gap or insulator, and this is just a non-superconducting material. And so the Cooper pairs, which are the charge carriers in superconductors, they can go through quantum tunneling when they go through this junction, and they obey certain equations, of course, called Josephson equations. And this has very interesting properties. So this is the actual picture under a microscope of Josephson junction in a qubit in our lab, right? So first thing to note is that, okay, so this gray area underneath is the sapphire or glass layer. So it's just an insulator. You don't really have to care about it. So this square area with these two markers, 1 and 2, this is sort of measuring the junction size, right? So this is the junction, and this vertical and the horizontal strips of metal, they are the superconductors. So in this case, the material is aluminum. So aluminum, one piece of aluminum at the bottom. And then we have the junction, which is aluminum oxide insulator, and then another piece of material, which is also aluminum. So this forms a junction, and I want you to notice sort of the scale, I suppose, of the junction. So the markers measure the junction size. It's given by 200 and 300 nanometers or so. So this is a tiny structure. Right. So finally, we are at what is SQUID? SQUID is just two Josephson junctions connected in parallel. It's interesting because if you consider, again, a loop enclosing this area, and the magnetic field through the SQUID must be quantized. And SQUID yields a straightforward way for us to control and measure this particular flux through this device. So the first demonstration will be observing the superconductivity in SQUID. So at a high temperature, if you look at the graph on the left, we see some sort of Ohm's law, which is V equals to IR, right? So if you plot a voltage versus current graph, then we're gonna have some constant gradient, which represents resistance. As you cool down, of course, this gradient is going to change. So you'll shift, you'll see some sort of a shift of the gradient. And then at some point, we're gonna see this bending of the graph, which indicates superconductivity in the middle. So here you have zero gradient, which means zero resistance. And these bending points are just critical currents. So it's when the superconductivity kind of breaks down when you have just too much current. Right. So before I jump into the demo video, this is the picture of the setup. And so this is the graph that you see on the oscilloscope, which we'll be looking at later. So this oscilloscope is just plotting the graph. It's just getting the data feed of voltage and current from this box, which communicates with SQUID to fetch the data, send and fetch the data. Right, so what we're gonna see is just voltage versus current graph. So this is the setup, and at the end of this rod is a squid. And this particular squid is made of YBCO, as we have seen earlier. We are using this particular superconductor because it has a pretty high critical temperature of 92 Kelvin, which means it's very easy to cool them just with liquid nitrogen, which is just lying around everywhere at home, everyone's home, which has 77 Kelvin of temperature. So it's sufficient. So when we put this into a liquid nitrogen and cool it down, you will start to see the graph is moving because the resistance is changing. And then at some point, we're going to see this bending behavior, right? So in the middle, you have zero resistance. And that's superconductivity you're looking at right there. So I'll just play that one more time because it's cool, literally. Okay, cool. Yeah, so the next demo, second demo, is flux quantization, right? So we have seen earlier that the flux through SQUID must be quantized. So if we apply any external flux that is not the quantization value, then it's going to induce some current in SQUID, which produces extra flux so that it can compensate for this external flux so that we meet this quantization condition. So the total flux must be quantized into flux quanta. Yeah, so this is pretty easy to understand. So this x-axis is the external flux and the y-axis is the induced current. So when we start from 0 and then start to increase this external flux, then it's gonna induce more current so that it sort of compensate and then cancel out this flux, external flux. So the total flux remains at 0, which meets the quantization. So as you increase beyond this half flux quantum, it sort of flips the direction, and then now it's assisting the external flux, right? So the total flux goes to 1 flux quantum until it reaches 1 flux quantum. If external flux matches this quantization condition, then you don't have any current because you don't need any extra flux for compensation. So this periodic behavior continues, but what we see in the demo will be voltage versus flux instead of current versus flux. So how do we get that? What we need is just some way to translate the two, which is using voltage versus current graph, right? So this bottom graph here is sort of what we have seen earlier, superconductivity, right? So this is the graph that corresponds to when the flux quantum, the total flux corresponds to integral multiple of flux quantum. And this top graph is n plus half, which is like half flux quanta, 3/2 of flux quanta, and so on. So let's say we start from 0 and then sort of fix the current value. Then we're gonna start from here. And then as we increase the flux from 0 to half the flux quanta, we're gonna transition from this point to that point. So, and then it goes back to this point when it reaches 1 flux quantum. So it goes back and forth. And so that is the graph that we are looking at right here. So in the experiment, But before that, let me just go through the setup. It has the identical setup, except we're just putting in voltage and flux instead of voltage and current. So that's what we see here. So y-axis is voltage and x-axis is flux. And here we're sort of like sweeping across the flux. So that box that we have seen earlier is sort of supplying different flux value, this value, and so on to the SQUID, and we're just plotting the voltage for each. Right, so we're gonna take a magnet and then just sort of put it near the SQUID. That's sort of supplying the external flux. And so I want you to take some time to think about what's gonna happen. And then in a minute, I'll play the video and see if your expectation matches. So that's a minute. So we're gonna take the magnet and then put it near the doer. And if you look at the graph, it's just sort of shifting left and right. Does this make sense? Well, if you guys know about graph manipulation or translation, this is exactly like X translation, right? So you have some flux here, X, and then you're just applying some constant value. So X becomes X minus X naught or something like that. So it's translating the graph in the X-axis. Right, I'll play that one more time. So one interesting thing to note here is that this flux quantum value, like the period here, from this point to this point is extremely small, right? Flux quantum is like h over 2e, and h is in the order of 10 to the power of negative 34, and e is negative 19, I think. So yeah, that's a really small magnetic flux. And so this SQUID can act as a very sensitive magnetic sensor. Yeah, mind you, this is like, it's a pretty strong magnet, but it's kind of far away from the SQUID, and it's kind of shielded by this thick doer. So it is very sensitive. So this is the same demonstration, except we're using a bigger magnet. So now the translation is going to be more drastic. Just playing once more. All right, cool stuff. So back to artificial atoms. I hope you still remember what Fernando presented. How is this SQUID thing is going to be, how is it going to be useful for superconducting qubits? Well, just to recap a little bit, this inductor capacitor circuit is equivalent of the metal strip that Fernando introduced, and it has sort of evenly spaced energy levels. And then when we replace inductor with a Josephson junction, we're gonna get this artificial atom. Of course, this is the symbol for Josephson junction. So now, if we replace this junction with a SQUID, which is just two junctions, just by putting some external flux, we can now control this qubit frequency. This is useful because controlling the energy level of the Josephson junction in fabrication is a challenge. So we can control this post-production in this way, which is pretty cool. And it can also be useful for doing some 2-qubit operation, for example. So say this qubit is coupled to another qubit, and then now we want to turn on and turn off this coupling dynamically. Then what we do is sort of move these 2 qubits away from each other in terms of frequency. So one has like very small energy, the other one has very large energy. Then when we address these qubits with microwaves, they are not going to interact very much. So it's easier for us to perform single qubit operations. And then now say we want to entangle these 2 qubits, then we will just put them closer in terms of frequency. So they'll have similar energies, and we can perform these 2-qubit operations. So sort of diagram of how the qubit frequency can change with the external flux. So at 0 external flux, we're going to have certain qubit frequency based on how the junction was fabricated. And then by changing the external flux, we can decrease this qubit frequency. And so we have this range of values we can play with the qubit. So that's all. I hope you enjoyed the presentation and hopefully learned something.
Hi guys, I'm Long. I'm doing PhD with the same lab at Nguyen, and we're kind of partner on this great thing. So I want to show you guys some example of a quantum system. If you remember, Fernando already talked about a qubit, which by a transmon, and Nguyen, let's say, underlined the SQUID with it a sensor. So there are a few fields in quantum technology here we have in CQT, with quantum computing and quantum sensing. I will leave the quantum sensing part aside and focusing on just showing you the quantum computer platform that will been realized now. So let's start with what Kunhi left off, the superconducting qubit. So this is what a big player look like for superconducting qubit. You see a really big chip with around 16 qubits and connect to each other. You can imagine controlling one qubit is really, how they call it, complicated. Getting all of them here, it could be a big challenge to just control and characterize. And they actually look really nice. If you look in the picture on the right, it's an actual qubit, what it look like. And you just shine light to them, they get a really nice reflection you see over here. So I would suggest you go into IBM website and Google website to read more information about superconducting qubit and the quantum processor. They are a really big player in the field right now, and going to be very interesting. Another platform is Sharp Iron, which is one of the also pioneer in the quantum computer. And the idea is a bit different. So the idea of Sharp Iron is that you actually put atom with I can say do some operation to turn it into iron. You trap them on top of the surface of a chip, and then you try to control them using laser and microwave. So it's a combination of the two. And the trap iron had the advantage of being really, really reliable in frequency and lifetime, but the controlling process is quite hard. You can see in the picture here, they're actually floating on top of the chip. You can imagine to keep them afloat and to control them at the same time is quite a challenge itself. So this is just a two platform, a two, let's say, famous platform. There's still more. We have ultra core ARM, which consists of a sample of atom cloud. Let me do this. Yeah, a sample of atomic cloud, which cool down to nanokelvin, and then you use that excitation of the atom cloud to try to do the computer. Another one is spin qubit in semiconductor system, which is really complicated. They use the 2D and 1D material structure to try to make a qubit out of it. Another one is nuclear magnetic resonance, which one also using, let's say, a natural qubit in nature with it a spin to quantum computing. It had a lot of advantages, but it had a challenging on control. And the final one is nitrogen vacancy center in diamond. So this one is a really interesting one, as in it can work at normal pressure and normal temperature. By all other systems, you have to put into specific condition for it to work reliably. So recap, around 6 systems: superconductors, trapped ion, Winter-Core atom, spin qubit, nuclear magnetic resonance, and nitrogen vacancy center. So in security, we had a lot of team doing in various systems. So for us, we had a large theory group and a large experimental lab. We focusing on supporting qubit, which is 2 lab by Professor Rainer and Professor Yvonne. Then we also have trapped ion by Professor Manas and Professor Dimitri. And surprisingly, for co-atom, we had a lot of group, at least 6, from Professor Lowe, Professor Kai, Professor Wenhu, Professor David, and Professor Travis. So just to show you that in CQT, we're focusing on a lot of areas, and many of them had advantages and disadvantages. So this is just a show to show you what we're doing, and hopefully spark you some interesting in the field.